All right. Welcome everyone to the final HPL seminar of 2023. Today it's my pleasure to introduce Reza Kakavand, a PhD student candidate with Amin Kameli. First thing, you might be confused. This is Reza K. That is Reza A. Then there's Reza H, who's not here. And then there's Reza D. So I'm pretty sure Amin just doesn't want to remember too many names. So he just hires people who are all named Reza. Makes it very easy. Better he just says Reza's assemble as if it's Transformers and they all just show up into some large morphine, machine. I don't know what your secret weapon is yet. Nonetheless, okay, so Reza is from Iran originally. He completed his undergraduate degree in mechanical engineering at the University of Tabriz in 2015. He then completed his master's degree in mechanical engineering at the University of Tehran, where he studied numerical analysis of human eye lens accommodation with application to presbyopia with Dr. Natzari. He then joined us at the University of Calgary in 2020, and he is supervised by Amin and Brent Edwards, where he's currently studying markerless motion capture and using it to predict joint kinetics using the bicycle that you see downstairs with all of the wires that are coming from it everywhere. Without further ado, then, I'll turn it over to Reza for his talk today, Enhancing the Efficiency of Subject-Specific Joint Biomechanical Simulations with Applications to Osteoarthritis.
Thank you. So the topic is enhancing the efficiency of subject-specific knee joint biomechanical simulations with applications to osteoarthritis. The knee has two long bones, femur and tibia, cartilages at the ends of the bone. There is this meniscus that acts as a cushion, stabilizes the motion of the knee. In details for the cartilage, if you take one element of the cartilage, we see this element, this cube element. We have 25% solid, 75% fluid. In solid, there are proteoglycans that are helpful in compression, and we have fibers that are in tension. There are two important zones here that I'm going to address in my lecture: superficial zone and deep zone. Deep zone is a region close to the bone surface, and superficial zone is a region close to the articular surface. So if that's the articular surface, which is the surface here that you see, and on the other side is the bone, and that's the femoral cartilage. For a complex environment like cartilage that has fibers, cells, and fluid, solid, there always are some problems, some insight that we want to have from this complex environment, and some problems that we want to predict. So we choose experiment. One way is to choose experiment to get the solution and the problem, whatever problem is. And that's sometimes too expensive and impossible to perform. So another way is to have a generalized model that is an adequate representation of this complex environment. And then we try to model every aspect of this complex environment based on our application. And we do simulation. So simulation is a process that we try to track the state of this model with time. So when you have this generalized model, you need to track it in time. And this simulation is risk-free and is interactive. By interactive, I mean when you see the outcome of the model, the expert can see the outcome. And if that's good enough, they say, okay, that's our outcome. But if not, they can add more details and say this approximation is a better solution. So you never get exact solution, it's approximation. Depending on the application, we see that this approximation is good enough. So for simulation, we have three major steps: material behavior, geometry, and motion capture. So for material behavior, we try to predict the behavior of the material in different loading conditions. So we know that some materials are soft, some materials are harder. So we know that the reaction from this material to the external load, to the external factors would be different. For our material and in our application, which is a mechanical approach, we need to include solid and fluids and fibers that have distinct pattern in superficial zone. These dashed lines that you see here are fibers, and they're parallel in the superficial zone and perpendicular to the bone in the deep zone. So we want our material behavior to address these details. We know that single phase, biphasic, and triphasic models have been applied to cartilage for simulation. Fiber distribution was modeled in 2D, and in this study, fiber remodeling was created. Fiber remodeling is when you assume that fibers are randomly oriented initially, and then you apply forces based on a criteria like maximum principal stress, maximum principal strain. You change the direction of these fibers by a small degree in each increment, and then to see if this fiber orientation converges or not. So we want to introduce a 3D model and do the fiber remodeling in a 3D space for the first step in simulation, which is material behavior. So the first objective would be developing a fiber remodeling model. The second major step in simulation is geometry. One common approach is to use MRIs and then extract or segment the region of interest from these MRIs. And here you see the result of segmentation. The current practice is manual, and it takes around 8 hours to segment bones and cartilages. So it's very time consuming. Recent studies have used automated methods like machine learning methods and statistical shape models. Machine learning models are intensity dependent, the intensity of the MRI. They're dependent on the intensity. Statistical shape models are dependent on the coordinates of the region of the interest. The problem with the statistical shape model is that the selection of the landmarks are manual. So depending on how many landmarks you're going to choose is again time consuming. And it's also dependent on the number of landmarks. The accuracy is dependent on the number of landmarks you want to choose. So if you want to choose a lot of landmarks, it's time consuming and it's not also reproducible. Like in previous 3-4 years, people try to combine these two, machine learning and a statistical shape model, to tackle the problems in each previous models. And they are very advanced models, but the problem is that they're not validated for finite element models. They're from computer science. So in our study, we want to propose machine learning plus a statistical shape model that is suitable for biomechanical model. The third step in simulation is, okay, you have material, you have geometry, but you need to do simulation to change the state of this model. If you want to change the state, you need to capture the motion of that. Okay, so we call that motion capture or mocap. The gold standard is marker-based motion capture. So you place some markers, they're reflective markers, and then you have some cameras, like 9, 10 cameras, and these cameras can track these reflective markers. So imagine you have a point cloud in the space, and they can track these markers with time. So if you have the location of each marker in the space, then you can, with time, then you can calculate velocity, you can calculate acceleration. So we call this kinematics, joint angles. And there is also something like a plate that measures the forces. So for example, you have a gate, you walk, and you definitely apply a force on the plate. So when you walk, you're applying a force on the ground, and also the ground would apply a force on you. So that would be your external force. And when you have the external force and kinematics, then you can measure the joint reactions and internal muscle forces. So we call this kinetics. But there is a problem with marker-based motion capture. As you see, you need an expert to perform this experiment. And it requires lab facilities. So it's limited to a lab, and the range of motion is limited. And it's expensive. You need cameras, you need force plates, you need reflective markers. And above all, it's very time consuming. So for single activity, it takes around 3 hours to complete, to capture that motion. So we want to use a semi-automated approach where we can use markerless motion capture. So in this markerless motion capture, you're not limited to the lab. You can take it out. And it doesn't have to be performed by an expert. It's not expensive compared to marker-based. And it's not time consuming at all. It's very fast. So there are 4 motivations in my study. First, having this 3D knee model where we can include fibers. The second would be automated knee segmentation rather than manual knee segmentation. And third is to find the knee joint forces. So once you have these 3, and then you can propose a damage model. The damage model can help for rehabilitation practices and to predict the damage in the knee. So all in all, we're trying to, again, go back to the topic, enhance the subject specific, trying to convert manual to automated, and then we want to use markerless motion capture. So these are the objectives: fiber remodeling, developing an automated pipeline for reconstructing the knee geometry, and lastly, estimating knee joint forces, moments using markerless motion capture. So again, I go back to each of these major steps in simulation in details for the methods and the results. So we have this 3D finite element model of knee is the cartilage is biphasic, fiber reinforced. And we wanted to investigate the effect of fiber orientation on the strain distribution of the cartilage. And then we said that, okay, we have this 3D distribution of fibers. Let's see why these fibers have this distinct pattern in cartilage, because they have a distinct pattern. And we wanted to see why that's the case. And because fibers are like cables, they are in tension, not compression. They're not, you cannot compress them. So we chose one criterion, and I'm gonna explain that criterion shortly. And then we applied that criterion, and we changed the orientation of the fibers that are randomly oriented first. And this is an unbiased model. We wanted them to be randomly oriented because we wanted to have one unbiased model. And then we applied this criterion to see if we get the actual distribution of fibers. So we compared the result with the experiment, and we got good agreement. So in this fiber remodeling, we apply a gate that has a force and a flexion angle. And the model has a 3D cartilage and meniscus. Cartilage is biphasic fiber reinforced. And fibers here you see are randomly oriented at each point. So they don't have any particular direction. And then we apply maximum stretch. So the criteria is the maximum stretch. And our hypothesis was that, okay, it makes sense. They are in tension. So they kind of withstand the stretch inside the cartilage. When you apply the force, there would be a stretch at each point. And they're kind of oriented in a way to withstand that stress and that stretch. And it turns out that this maximum stretch is aligned with the maximum strain and maximum stress. So here is the result for femoral cartilage in the superficial zone. And here is the final distribution. It starts from random state and then final result. We also investigated this in the depth-wise orientation, and we saw that parallel distribution of fibers in the superficial zone and the perpendicular fiber distribution in the deep zone. So we have this material behavior advanced model, fiber reinforced, fluid, solid. Now we want to enhance the segmentation of geometry. So the first part of this second objective would be focused on the bones. And the second part, we will automatically segment cartilages, but it's still in progress. Here, I'm going to just present the results for bones. So we have MRIs from 507 individuals. So we're going to propose one semi-automated model that segments femur and tibia. And we want to validate this model with manual segmentation. So the ground truth would be the manual segmentation. And then we would add cartilages and meniscus to these bones. And we create a finite element model from semi-automated segmentation and another finite element model from manual segmentation. And we compare the mechanical results for these. The model that we introduced was 3D Swin unit R segmentation. And the brain behind that is Payman, sitting at the end of the class. This model was introduced 2022 and was applied to brain first. And then we use this model and adapt it to bones and cartilages. And then we get the outcome of the machine learning segmentation model. The geometry is not smooth, really. It's not suitable for finite element. So we apply a statistical shape model to smooth this geometry and to make it suitable for simulation. And from manual segmentation, we have manual segmentation of femur and tibia. We get the geometry of the bones from both sides. And we did the manual smoothing and repairing and cleaning the geometry from mesh lab, in mesh lab. Then we add cartilages, menisci and ligaments to this. So ligaments, menisci, and cartilages are the same in both models. We perform the simulation of walking or gait, and then we compare the mechanical results. So here I present the results from Swin Unitar, MRI. This is the manual segmentation. It's kind of rotated by 90 degrees. And here you see the results for one slice. So MRI has 160 slices in our case, but here just showed it in a large size so we can see the results. The evaluation metrics that I used were dye similarity and Hausdorff distance. Dye similarity is intersection over union. So intersection over union. It shows how close your segmentation is to the ground truth, which is the manual segmentation. And we got over 98% of the accuracy, and it's comparable to other most advanced studies, this accuracy. And the Hausdorff is in millimeter. So this is kind of, we use the intensity and the pixels to compare. And this one is in millimeter, and it's the maximum distance between corresponding points on the automated segmentation and manual segmentation, the maximum distance. And it's a little bit larger than the resolution. It's a little bit larger than the resolution. And then we apply SSM to fix the artifacts, to fill the holes that created from Swin Unitar. Sometimes in some slices, we have some holes, we have some artifacts. It comes and fills those, and also it gives you a smooth surface. And interestingly is that we don't lose the accuracy when we apply SSM. And even here, I think it's by chance we have improved the dyes. But the important message here is that you don't lose the accuracy of your model. Here is the maximum principal stress distribution between manual and semi-automated in medial and lateral cartilages. So both on the surface and depth wise, and this is a cross section from the maximum value of the mechanical parameter. So for example, here and here are these cross sections. So we did the same for most common mechanical results, mechanical parameters like maximum principal strain, fiber strain, contact area, and fluid pressure. So here is the numerical comparison. The manual is the solid line with the circle, and the semi-automated result is the dashed line. They are really close to each other. And the dotted line is the absolute error between two models. So here we are in the superficial zone. The average shows the average of this mechanical parameter on the nodes of the contact. So when you simulate the femoral cartilage comes in to contact with tibial cartilage, and there would be a contact area, the average of this mechanical parameter on the nodes of this contact is the average, called average, and the peak is the maximum of this mechanical parameter in the contact region. So this is throughout the time for the gate, and they're not statistically significantly different. We did the same for the dip zone, where cartilage interacts with the bone. And again, they're not significantly different. So now we have material behavior and advanced model, fiber reinforced biphasic, and we introduce an automated segmentation for geometry. Now we want to capture the motion and get the kinematics, kinetics. The software that we use is OpenCap. It's open source, it's free, it's a web app. It uses at least 2 iPhones. In the first step, it uses one pose detector. And right now the options are HRNet and OpenPose, these 2 pose detectors. So what they do, they track the 2D key points in each time frame. And then in OpenCap, there is a machine learning algorithm that converts these 2D from each camera to a 3D markers. And once you have these 3D markers, kinematics are automatically calculated. So you don't need to go and calculate kinematics yourself. But for kinetics, you need to either download the Python scripts and run the Python scripts, or you can use OpenSim. You have kinematics, you have the force plate, and you can use OpenSim to get the kinetics. The problem with these markerless motion captures is that you need to validate the motion that you're going to capture first. You cannot say, okay, I'm going to use this for whatever activity I want. So we know that cut, squat, run, and jump activities have been validated using OpenCap. But in my research, we're going to validate this software for cycling. So we are using 4 iPhone cameras to improve the accuracy instead of 2. There are pedal sensors, and these pedal sensors give you 3 forces in local coordinates and 3 moments. In local and global coordinate is the center of the crank here. And there is another sensor encoder that measures the position of the pedal and the crank at each time. And we want to validate this with marker-based motion capture. We have 32 markers in lower extremity and 9 to 10 cameras. We want to track these 32 markers. And then we compare kinematics and kinetics from OpenCap and from marker-based OpenCap. So here, I want to show you the time that you can save using mocap, Markell's mocap. Here, the rectangle shows the steps that you need in OpenCap. It takes around 15 minutes, calibration and data collection. Compared to marker-based, you need these two steps, instrumentation and marker labeling. And for cycling, it's 3 hours compared to 15 minutes. So here I show just 3 kinematic parameters. This study is still in progress. So here is the hip flexion, knee flexion, ankle flexion, and they're not statistically different. But this is only for a couple of subjects. We need more subjects to completely make sure that this works. So all in all, we have 3 steps. We introduced 3 steps. In material behavior, we had fiber reinforced biphasic model, and that also model from Salvatore. We just adapted to the 3D model. And then we automated the process of segmentation for bone and cartilage. And in this second step, the time for automated segmentation is 10 minutes compared to 2 hours, compared to 8 hours of manual segmentation. And in the last step, we have motion capture for loading. So we want to estimate and measure the internal forces in the knee, the joint reactions for our model. When you combine all these, you see that we get subject-specific 3D knee. It's kind of enhancing. Maybe it's not completely subject-specific, but we're just trying to push the boundary a little bit further. Okay, that was all. Thank you for listening.
Great. Floor is now open for questions. Would you like to start?
I was wondering if, like, for your, you said it was a fiber reinforced composite material. In terms of determining material properties, like for the fibers as well as like the base materials, like where are those?
Yeah. So this model was introduced by Salvatore. They have compressive experiments. They try to see the deformation and forces in compression, and then kind of feed their model that is fiber reinforced to those experiments.
So it's based on, rather than like measuring the properties of the components, like the fibers and then the surrounding material.
Yeah.
It's measuring them together, and then you do some kind of like optimization.
Yeah, exactly.
The same result.
Exactly.
Great talk. I have a question about the last part of your presentation.
Yeah.
When you say OpenCap was validated for all these tests, you mean validated to output joint reaction force or other variables? For example, has OpenCap been validated against instrumented prostheses where you can measure directly the joint reaction forces?
No, it's so when we validate, we say that marker base is the ground truth for us,
right?
And we use the coordinates from marker based, and then we have the we haven't validated kinetics. I just showed the kinematics because I think it's just the exact same process for both if they're good in kinematics, because the force would be the same for both of them. So we get the kinematics from marker based using OpenSync. So if you get the coordinates, and then you can use OpenSim to get the kinematics. But in OpenCAV just gives you the kinematics.
So what model are you using from?
Sorry?
What model are you using? A full body model
FE for OpenSim.
for OpenSim? Is a full body model or just lower extremity?
I think it's full body. Yeah, it's full body.
And does it consider the knee as a hinge joint, or because I think you showed the
Okay. This one?
no, I think you showed the picture and the knee as I think was a hinge, or do
Hinge.
you think it models as a 3D joint?
I didn't get your question. This question.
So the knee joint, this model that they're using OpenCAV,
Yeah.
it considers the 3 degrees of freedom of the knee or just the flexion extension?
No, the 3D.
Okay.
It's 3D.
Right.
It's 3D. It cannot capture 2D. In fact, just 3D. So if you just want to capture the sagittal plane, it confuses.
Yeah, I know, but
It's
in
confusing.
the model itself, you can strain the other degrees of
Oh,
freedom.
no,
Yeah.
we didn't do that.
Okay.
We made it. That. Yeah.
You have a question?
Yeah, so this OpenCAV like tool is just based on like videos that you provide to the system, right? So
Yeah.
you don't provide any information about forces, external forces and moments.
And no.
So how does it predict joint forces and muscle forces?
For kinetics, yeah, you need to have the forces, pedal forces, but for kinematics, you don't need forces. You just need the coordinates.
Okay, so if you want to measure, if you want to study kinetics, then you have to provide external forces
Yeah.
to the OpenCAV.
Yeah.
You cannot predict. Okay.
No, you cannot predict. For some activities like gait and jump, things like that, they can approximate it without force plate. So they have some models from studies, from previous studies. So based on body weight and height, it just predicts, it's an approximation. But for cycling, they don't have that model.
You mentioned at the beginning that it is exact and push the
Mhm.
cushion.
Cushion.
Can you later on explain to me mechanically how that works?
Sorry, the last one.
Explain to me mechanically
Oh,
how
okay.
that works, that the meniscus acts and pushes.
So
Let's leave that. We can do that.
okay, first.
Can you go to the comparison between the markerless result and the markerless result? Yeah, these one. And you say the true values are the marker-based results.
Yeah.
I would suggest they are not.
Mhm.
I would suggest that if anything, the markerless results are more accurate than the marker-based results.
Mm.
And we have done some measurements in vivo where we have quantified angles and movement of the lower extremities. Marker-based and not marker-based.
Mm. Yeah.
You know, if you look at the lowest,
Mhm.
the ankle flexion, you have a problem there.
Mm-hmm. Yeah, the difference here is large.
So what do you suggest then if you want to compare like, the result of OpenCAV?
I don't know which one is the gold standard. And I think
The marker base is the black dotted.
We assume that marker base is accurate and it is our standard. We assume that marker based model is our standard instead of
and I suggest that.
Yeah.
So
Okay, so what do you propose to the?
I don't know.
Okay,
I just the gut feeling is that it's worse when you go with the marker because when you put one marker a little bit more to the right.
Yeah. I
And
agree.
Usually, here you have degrees, 5 degrees in some cases.
Yeah.
Different. That's probably about 3-4 millimeters.
Yeah, I agree what you say, but that's just something that we have right now. And even people in Stanford University, they validated the results using marker-based. No, I mean the university that
I would
proposed
rather,
this.
I would rather face a system where I know exactly the
Yeah.
solution.
Yeah.
And have then the two methodologies tested.
Mhm.
And then see which one is closer.
Yeah.
So I spoke to Stanford about validating their open cap system against the fluoroscopy. They did not seem interested, I think, because they know it's probably not that accurate. None of these markerless systems have done that. Or they have done it and they haven't published it because it's not great.
With
Yeah,
what?
I mean, you will get pushback. What Benno says, I mean, when you go to publish this, that you'll get that same argument, and it's a good argument. And
Mhm.
Selby, who owns Data, makes that argument all the time.
Mhm.
Is marker-based motion analysis the ground truth? No. Should it be? No. Should it be dual fluoro? Probably not. Like, unless you want to validate a very small piece of the puzzle.
Mhm.
Want to take 10 years. But yeah, it's
That kind of leads into, man sitting behind you, Brent, who Andy's work, all of the probability distributions, right? We have no true answer. Everything's just.
So,
going somewhere
I
with
mean,
it.
one point is that we've been using motion capture marker-based. It's kind of a de facto standard. Everyone uses that for capturing the motion. And right now, with all these experiments that we've had in this, we want to replace it. Okay, we want to replace that. So we want to say, okay, we get the same result from that.
I'll tell you what,
But-
if we can't accurately calculate hip flexion, knee flexion, and ankle flexion when somebody rides a bicycle, this field is in big trouble. So, for sure, calling it gold standard, if you're talking about transverse motion and frontal plane motion, I think is completely debatable. But if we can't accurately quantify sagittal plane joint angles in somebody's cycles,
With what?
I'm just saying, like, in this circumstance,
What is accurate?
true. What does accurate mean to you?
No,
Depends on
I
the
mean,
application.
with what do you
No, accurate.
accurately measure that? What
Alright.
is the,
Here,
The actual, the truth.
Hi Reza, thank you so much.
Mm.
I just want to understand how the video of without the marker, you analyze and then compare with marker based.
Mm.
How you do that analysis? Because with a marker based, you know specific angles and specific locations, right?
Mhm.
In markerless, how you do exactly at that particular point and then do the analysis and then compare
That's a good question.
plot
Yeah.
both in one graph
Yeah, that's a
and
good.
they're almost same in your plot,
Yeah.
right?
So the thing is that they have already one template, like a template, and tries to fit to the person's body, that template. And this template, or we can say the machine learning, has been trained for many individuals, so many people, especially this open pose detector, which has like 10,000 citations. They were just published in 2017. So it's a very robust pose detector. And then this OpenCap, they have a template for like 63 markers. So it's the inside the model, the markers like this markers. of like 63 markers. And their name, the landmarks, the name is just famous. We know that this landmark indicates, for example, the femur or the shank. And then we try to say, okay, this marker represents that, and then we compare these two. But it's again an approximation, yeah, because it's hard to find the landmark. It's not reproducible, as Benno said. It's it's not the something that we are sure. But
So it's the model
yeah.
that already published and it is well defined and
Yes.
accurately done.
Yeah.
So you're using that model and getting the result and comparing with a motion based.
Exactly. Yeah.
If that is 100% correct, then why do we have to compare with the motion based? Just trying to understand.
This
If that is
open
done
pose
lot of
detector
times,
is just 2D. It's just one screen. So, but for getting the dynamics and kinematics, you need it in 3D space. So you need 2 cameras. So you need the position of that marker in a 3D space. Okay, that's where the contribution of OpenCAD is mostly. Other than that, other than this, the rest is just from other studies. It's been there before.
Yes.
I missed the beginning of the presentation.
Yeah.
And so is the question that you want to know the material properties, geometry, and then kinematics, kinetics, and then for any movement, or based on what you train your model to do, you want to predict what's happening inside the knee joint, and then if there's too much stress, less stress, etc.
Exactly.
The aim of the whole.
Exactly. Yeah.
Andy, Tila,
Sort of on this big picture idea that trying to get the stresses in the cartilage. Going back to your cartilage model, I would have thought that would be most sensitive to the compressive forces that are being applied. And so when we go to now this level of, say, markerless or even just marker-based motion capture, and with an open sim model, most of those models, as you mentioned, were at 3 degrees of freedom at the knee, so just rotations.
Mhm.
Would you not need 6 degrees of freedom at the knee? So rotations and translations?
For the model, yeah, for the model, yeah, but that gate that I showed you before, it was just a template course. They just assume that the other rotations are negligible, and this is what they apply to it. But yes, for our application, we want to have a 3D force and loading too. Yeah. That's the difference.
Tila?
I would like to come back to that markerless towards marker-based comparison. And you, in passing, you mentioned somewhere there's no statistical difference between the two.
Mhm.
But should that really be the question if you're trying to measure the same thing? So you should actually have a completely different hypothesis. Your hypothesis should be that they are different, and you're testing that they're not different. So you need to sort of think about a method comparison study. I'm not sure what statistics you've done on your comparison. That's in essence my question.
Mm-hmm. So I mean, the type of a statistical analysis is important for that. Yeah.
Yeah. So
That's it.
just so have you? So you said you
I
had
think-
no statistically significant difference. So did you just do a t-test, or
No, there is a mapping statistical analysis. It's a
Okay.
mapping that tries to compare the matrices instead of a one column. So in t-test, you're just comparing one
Yeah.
column. But in this statistical shape, in this statistical analysis, you're comparing the whole data with the other one.
okay, but your hypothesis is still. If your hypothesis testing is still set up in the same way as a t-test, the t-test would try and find a difference, versus you actually want to find a non-difference. So I think have some more thoughts about your statistics if you do.
Okay.
Venom?
If I would have had to present that, so I would have probably done it differently. I would have said, here I have a new methodology. It does this.
Mm.
And I want to compare this methodology with some other things.
Mhm.
Discuss, for instance, the effect of open sim on the results and so on. Basically more present the new methodology and discussing the strengths.
Mhm.
Because, you talk about validation, but you cannot validate.
Mhm.
But if you compare methodologies, you may be able to say something about the accuracy that you can expect.
Yeah, but to be honest, when you want to do that and publish a paper, they say, did you validate it or not? And if you haven't done that, I would be really happy to just do that because to be honest, it's less trouble because you need to market base is a lot of trouble. You need to reserve the space. You need to do market base. With that, I could just test 100 individuals so far. But I would be happy to do that and to just go inside the OpenCap and the details of that and the troubles that we have faced a lot to get that result. It's not just easy to just set up 4 cameras there and say that this works. Not like that. It takes a lot of tests and trials to get the stable results. But in the system that we have, you need to take this a step first and then go with that the other one too.
So, Min, do you have a question?
Yeah.
Okay, and then Arash, and then Steph, and then Brett.
If we're gonna stay on this topic though, let's not start something else, because I have questions about markers. Okay, go ahead. Okay, can you go back to the result from the marker list? The hip's the best, the knee's the second best, and the ankle's the third best.
Mm.
Or the hip's the best, the knee's the second worst, and the ankle's the third worst, however you want to say. So what I think is happening is that this model needs to call something ground. It needs to call something the center of your coordinate system. And I think what it's doing is it's calling the pelvis or the hip the center of your coordinate system. Everything else is relative then to that. And I do think it's using a constrained model. I do think it has a hinge joint at the knee. And I think these are things that you have to do to make the machine learning algorithm work correctly. Otherwise, you could end up with feet on top of people's heads and knees that are way down here and stuff like that. So what I think is happening is you have the most accuracy at the hip, and then you introduce a little bit of accuracy when you're trying to predict the location of the thigh. And then the shank is relative to the thigh. You introduce more error there. And then the foot is relative to the shank. So that's just a comment. That's what I think is happening. I don't know if that's what's happening. It could be that the algorithm has more trouble with the ankle. Maybe the bike gets in the way or something. That doesn't really make too much sense to me.
So do you think we have proposed the machine learning model or the OpenCap?
I do not think that
You said
proposed
machine
the
learning.
machine
No, we didn't. So
No.
we don't have access to the machine learning.
Yeah.
We don't have that access.
Sorry, yeah, that's not what I'm saying. I'm saying that I know how this model works,
Mhm.
and I'm saying this is why the greatest amount of errors at the ankle
Yeah.
and the least is at the
And also, the rate of motion here is really high. So,
what?
and
3 hertz?
the open pose or the pose detector has a problem there.
Okay.
The first step
What's
in
the
that.
cadence? Do
Sorry,
you know? Do you remember the cadence?
the cadence. Reza, do you know the cadence? The
One
RPM?
cycle every 2 seconds?
It's going to be less than 100 hertz.
I think around 60 to 90 degree, 90 RPM.
Okay. Okay, no, I just wanted, so you don't think, is the open cap, does it interface at all with the open sim source code
For kinematics.
for that?
Yeah, for
Okay,
kinematics
and
does.
I think this is exactly what's happening.
Yeah, it was automatic.
Anyone else on this line?
Can I just follow up on that? For example, one way I think to check, so you scale the model, right? You did the scaling process.
Yeah, for marker base, yeah,
Yeah.
but for
So
marker,
what's the error there? So, I mean, after you scale the model, even visually you see if the model changed the knee or the ankle were realistic to the truth. So for example, you visually compare the model, the output of the scaling and a picture from your subject. If the model placed the joints in an unrealistic posture, just to adjust, to minimize.
we have seen that, yeah. We first detect if that motion is smooth, if it's stable or not. Sometimes you have like a lag or the jump. Yeah, in OpenCam you have that a lot, but it's really sensitive to the color of the clothes. Should be contrast to the ground and the bicycle, and it's also really sensitive to the position of the cameras. There are instructions for that. That's why we are limited to the number of cameras. We use 4 only. That's the maximum possible we can go. But if you have like 7, it gets confused.
Are we off the marker with motion capture or Robin
Should
has
be.
one?
Could it be due to the position of your subject on the screen? Like, assume like your screen and what it's getting is flat, but you know, you got like curved effects on different cameras. So it's not a fisheye, obviously, but maybe your ankle is more like to the edge of your screen and you got distortion.
Mhm.
Depending on your phone, I don't know if you got like for like the last iPhone or something more, something older, but
Mhm.
it might also be due like your hip is right in the middle of the screen, what you got is flat and close to reality, and what you got on your edges is like more distorted. Could be also
To the edge of camera, you mean?
Yeah. Because you actually need to flat.
iPhones, you mean
Yeah.
iPhones?
Maybe, yeah.
We try to have like a lot of boundaries around the, so it's kind of at the center.
Okay.
It would not really get close to the edge. But you're right. If you do that, we had this problem.
Okay, done with marking with motion capture. I'll get my point in about this, which I think this is the least important step of your whole process, and I think the least relevant. Like, who cares what the motion is? If you're getting away, it's probably because you have something happening with cartilage levels, split line patterns, or you have a difference in, some sort of inflammatory response. I don't think any of us are ever going to predict someone who gets away by measuring kinematics. I think we're just wasting our time.
Yeah.
And I don't know, and I think so. I don't know. Personally, I think you can just deal with this and go, yeah, there's some error, move on. To
Yeah.
the rest of the stuff that's clearly more
Yeah.
sensitive.
And that was, to be honest, the smallest portion of my study, like around 4 or 5 months. The rest was like 3 years, the first 2 parts.
Have you ever seen how predictive the external knee adduction moment is of away
Yeah, that's a force.
progression?
That's not a kinematic, that's a
Okay,
kinetic.
it's basically a kinematic variable. It's external moment.
I mean, if it was really predictive, I mean, it is predictive, but we're not sitting out there looking at people and saying, you're gonna get away, so we should bring you into the hospital first. I mean, we're good at retrospectively predicting.
All right, I can talk about split lines if you want me to
Yes.
talk about it.
More statistical shape models, please.
Um,
Actually, let's see. Yeah.
I do have a question about the split line study. Did you just drive it? Was there hydrostatic pressure? Was that part of the loads in the finite element model?
You mean inside the cartilage?
Inside, yeah.
Inside is considered inside the model.
So what happens, I'm just curious.
Inside the model is considered.
Yeah, what happens if you have a total random split line distribution? And then you don't simulate gate, but you just put in the pressure, the hydrostatic pressure.
The
Do
pressure.
do they evolve? Or remodel, I mean, that's a better word, remodel.
Yeah, they
And
do,
they
but
remodel
but
considerably
it's
different from the
not it's not as accurate as the
gate,
gate.
as adding the gate.
Yeah.
What about if you just added the gate alone without the hydrostatic pressure?
The hydrostatic pressure is inside the model. I mean,
Yeah.
the equation that Salvatore proposed
Yeah.
is inside that. I haven't changed that. I don't know.
I think if you apply only hydrostatic pressure, you will get fiber distribution for sure, but it may not be that similar to what you have like
Yeah.
But we have modeled it in single phase, solid, just solid. We didn't see the distribution, if you mean
Yeah,
that.
No, has anybody ever looked at split line development in like a growing pig or like a large animal? And like see if it's like, if the orientation's locked in at like childhood or if it changes over decades?
I think it's pretty quick. For pig, I know there are studies, and they have just shown the split lines with the ink.
Yeah,
with
no.
the ink. I think it's pretty fast, like 2 years, I guess.
Yeah, but pig's probably like fully grown in 2 years.
Yeah. I mean, if it's 6 months, it's not gonna work, or 3 months. They're not fully grown.
I just have a question about the model, and this is also based on not being super familiar with like cartilage properties and things, and behavior. But is your model quasi static? And do you think like in a situation like standing that might be reasonable, but is it also reasonable for like more dynamic movements like gait or cycling?
I think the model is dynamic. It's not quasi-static. It is dynamic.
So it has like tissue acceleration within the continuum model?
That's a good question. No, it doesn't have. I think it is quasi-static. Yeah, you're right.
Like just from.
So it's just a mass kind of you're ignoring, I guess.
Well,
Yes.
just like I guess with the quasi-static, it's assuming that there's like small deformations and it's small enough that you can kind of neglect changing.
The acceleration. Mhm.
But I don't know, like, this is from my
Yeah.
background in muscle where things are just
Right.
changing a lot, whereas I don't know if that's the case also with cartilage. Or if it's reasonable to assume that it's quasi-static.
Yeah, that's a good question. I don't know if Amin has.
Yeah, we call it dynamics because we consider the effect of fluid pressure. Otherwise, it's like quasi-static. But there's no acceleration working.
So there's experimental studies that show like the like accelerations or like deformations of the tissue over time. Is that such a thing? Is that a thing that people can get?
We kind of show the deformation with time, but we just don't introduce the accelerations. Maybe it's kind of included in the force that is applied because the rate of force changes. Maybe it
like
is the force that we apply a boundary condition. Maybe it's kind of introduced the effect of deformation.
So it's good. Curious to know if we have to understand the elbow joint movements or any kinetics or kinematics with that. Does your model will help to do that? If not, then what else we need to change in order to do that understanding?
Elbow.
Let's say you did
To be honest,
right
this
now,
yeah.
not me, something else. What has to be changed?
I think the geometry definitely, the middle one is not going to work for that at all.
Only the geometry?
the geometry not going to work. And I think the material property is only validated for knee. I don't know if it's also valid for elbow cartilage or not. To be honest.
Okay, so you have to change everything. Material property,
Yeah, everything.
geometry,
Yeah, yeah.
And even the third one,
Yeah.
markerless capture.
Markerless motion capture, you just need to change the activity. You just need more markers in the elbow. The OpenCAV would consider markers here. It's just a validation, we need markers here, but for OpenCAV, they have markers here, so you can capture the motion of the elbow with that.
My question is regarding the second study, like auto segmentation. So we have this machine learning model that auto segment for your bone geometry, but it's not smooth. And then you have SSM to smooth the surface, right?
Yeah.
My question is that sometimes we need those roughness in the model. Let's say there's like fracture or something, and you don't want to like miss it. So what would be your solution for that?
That's a good one. For bone, we have right now, or recently, I developed a script for a smoothing, just a smoothing. I mean, the filtering, not a smoothing. It filters, it just considers a point cloud and fits to the bone. For example, you have like a, I don't know what's the disease for bone growth, you know. But for cartilage, we're not gonna apply SSM because you have like a hole and it's OA. We're gonna apply this script that just tries to filter, not fill the holes. It's just smooth. But the roughness for finite element, to create the elements, we need a little bit of smoothness there.
So we have different, like another option than the SSM.
Yeah, yeah, exactly. Yeah, we have.
Follow up on that. So if you're proposing to look at osteoarthritic knees that have osteophyte,
Yeah,
and
osteophyte.
you need smoothness, like how do you balance those two? Do you get rid of the osteophyte and is it valid without osteophyte?
Yeah, if it's healthy, we can use this model, the segmentation model. But if it's not healthy, we have the second approach, which is this Python script. It would feed a point cloud to this, and then reconstruct this surface with this point cloud. So the roughness would go away, but you still have the osteophytes.
But does that mean you have to know beforehand whether it's healthy or diseased, which model you apply?
Yeah. Definitely, they have a pain.
There are better tools, right? Like you don't need to use MRIs to develop a statistical shape model. The idea is that you could build it off using a DEXA scan, which is cheap and readily available pretty much everywhere. I mean, it's just at the beginning when you develop these statistical shape models, you need to use the highest resolution images that you can possibly get. But that doesn't mean that it's the only option. And it's, Brent and Olivia's did a whole lot of work with, externally based markers to try to create the same thing. Sure, it wasn't so great, but it also wasn't the worst thing in the world. It's still relatively normal. Do we have any final questions for Min? Raise.
Let's ask a minute.
Okay, if not, then we'll see you next semester. It's January. Not 11th.
Yeah.
7th, 11th is the first one.
11.
Yeah, 11th is the first one, and it's Pablo Fleitas, who's a PhD candidate with Juan Murias. He's working analogous with John Lash, and he's going to talk about exercise physiology. So we'll see you all then. Thank you very much. Enjoy.